So we're learning about thin film interference, and we're going to video it. You have a piece of glass, let's say, with a very thin film of water on top. The glass has a refractive index of 1.55. By the way, what does refractive index mean? It's actually a measure of how much light slows down in the material. That's what refractive index really is. So if the speed of light in air is 2.99 times 10 to the 8 meters per second, if you take that speed of light and you divide by 1.55, that will be the speed of the light going through the glass. So this is strange, right? You've actually never seen light travel at the speed of light. Why not? Because you're always in the air, right? It's really close. In the air, it's very close to in a vacuum, but it's not quite. It's 1.001 or something like that. We take it as negligible difference. When light goes through water or glass, it's gonna slow down. That doesn't really matter for us if it's going straight, perpendicular, but if it's at an angle, that is going to create what? Have I taught you guys refraction? Okay, I'm just gonna teach you refraction. Take your hands like this. Pretend you're holding a wheelbarrow. Do you know what a wheelbarrow is? Yes. Okay, you lift it up and you carry stuff in it, right? Now this particular wheelbarrow doesn't have one wheel, it has two wheels in the front. Okay? And you're gonna push that wheelbarrow. If you go straight from smooth into mud, so you're on the road or something and there's like a muddy patch, and you go into the mud and you go, what's gonna happen? You're gonna slow down in the mud, right? When you come out of the mud, what happens? Then you speed up again, right? Okay, fine. Well, what if you come to the mud at an angle? Oh, I'm not in the video. I'm back. What if you come to the edge of the mud, like if my counter here is the edge of muddiness, and I'm like this, and I'm wheeling my wheelbarrow in, and I hit the mud.
One side speeds up faster.
This side hits first, right? So it hits the mud and slows. But the other side is still on the road.
It's fast.
So you turn into the mud, right? That's my funny little explanation of refraction. So you can think of it like a beam of light has a width. And so if you think of this as having two sides, this side is going to hit first. It's going to slow down, and the only way for light to keep going the same speed, which it has to do, it's going to turn, right? So this is going to do something like that. It's going to refract into that material. When you go into a more dense material, are you going to refract towards the normal or away from the normal? You're going to refract towards the normal. Do you understand what the normal is? What's the normal line? The normal is perpendicular, right? There's an angle here. What would I call that angle? Good. This is the angle of incidence. So it's the angle on the way in. It's incident to the material. So we call it the angle of incidence. And then this straight here. This is going to have an angle as well. What do we call that?
R.
Yeah, this is the angle of refraction. Who remembers Snell's law? Did you guys learn this? Yeah?
Yes.
You just don't remember it? You know it, Farzan?
Yeah.
Go ahead.
So, n of incident times the sine of incident angle equals to the n of reflection times the sine of their reflection angle.
Yeah, okay. I would do it, I would say it like this. Where n is refractive index of the material. And this theta is the angle to normal. Okay. So n1 sine theta 1 equals n2 sine theta 2. And of course you can rearrange that however you like. Can they see that on the video? No? I need to zoom out a little bit maybe. There. Okay, so if I told you the wave, well, I should ask you, if I draw this and I gave you the angle of incidence, what would you need to know to find the refraction angle of refraction?
The n of the air.
Okay, so you need the n for the air, you need the n for the water,
They have the angle.
and you need the angle of incidence, right? Does it matter the wavelength of light that's coming at you? No. Okay. Now, you're going to hit the glass and you're going to reflect, right? Well, some of it will reflect. Some of it's going to refract into the glass, but some of it's going to reflect out like this. Oh, I should have drawn that a little bit steeper, sorry. Because this is refracted, so it's that. What's going to happen? So this is the refracted beam incident through the glass and then reflected back towards the surface. What's going to happen when it leaves the water and goes back into the air? Good. It's the opposite. Now we're coming out of the mud, right? So the top side kind of hits first and speeds up in the air, and it goes, and it turns out, and it's kind of the opposite refraction out. These two beams, if the film is thin, will be very close together. So what might you expect to happen with two beams of light very close together? Who said interference? Somebody did. Thank you, Leon. Good. So they're going to interfere with each other, right? So you're going to have different spots of brightness. Okay, there's something you have to remember here. This, and I've drawn this as if this is like a big angle and they look far apart in the drawing. In reality, these are right beside each other, and the angle of refraction is almost vertical, right? The wavelength of the light in the water is it going to be the same as the wavelength out here in the air? Turn to the person beside you and decide the answer to that.
Because like air slows down. Light, even
Does it stay the same? Who thinks yes, it stays the same? Okay, who thinks it changes? Okay, you win today. The wavelength of the light changes, and I'll tell you why. It's not super intuitive. It changes because it basically changes because the speed changes. So if you have light going to a surface, boom, and it slows down. You know the universal wave equation? B equals lambda f. Let's give Sufi a golf clap. This is the universal wave equation. What does this work for? Only light? Waves. Any wave. And light is a wave. Right? No matter what Einstein says. We don't know if it's a wave. But it acts like a wave a lot of the time. Okay, so if this is true, then ask yourself this. Put your hand like this. Let's say this is your barrier between air and water, and these are waves. When it leaves, is the frequency of waves coming in the same as the frequency of waves going past the boundary? Lucas is nodding. Yeah, it has to be, right? A wave front, a crest is not just going to disappear, right? And you're not going to just have a crest pop out of nowhere. So if 3 crests per second hit here, then 3 crests per second must leave. Frequency has to be the same before the barrier and after the barrier. What about velocity? Not the same. So if my velocity is getting less, what has to happen to my wavelength? Also less. So you're going to shorten up a little bit. Okay, that's tricky business number 1. Things you have to remember. And I'll explain number 2. I won't assume that you guys know this. Who can film? Oh, this is part 1. Part 1's done.